1986, while on a construction site, he accidentally jackhammered into 30,000 volts of electricity, 15 times the amount in the electric chair.
Most of the wounds were to my leg area, where I had a third of the knee joint burned away on both legs. He had 2 massive gaping holes in both legs. You know, surviving, I'm surprised. Not losing his legs, I'm stunned. The paramedics got back in the hospital and said that they actually revived him. Not only was I shocked, but I was almost wondering, what kind of life's he going to live. It was a very difficult time for myself and my family. I was going to have my legs amputated, and it was the persistence of my mother and father to go out there and seek out a physician that would be able to save my legs. It was kind of a bleak time for myself and my family.
After 3 years, more than 15 surgeries, and against all odds, Milo was walking without crutches.
At first, it was my dream to be able to run again, so that was kind of the driving factor for me to go into the gym, go to rehab, and keep pushing and pushing. And then I kind of found out that, I wasn't going to be able to run again, so I kind of thought, well, if I do sports that involve the upper body, I can maximize myself that way. That's how I got into kayak paddling.
Paddling became an integral part of Cliff's rehabilitation, helping to strengthen him physically and heal him emotionally.
I love challenges. The more effort that you put into the sport, the better the outcome is going to be.
Cliff's determination and passion led to an outcome that is the ultimate for any athlete, a spot on the U.S. Olympic team. He competed in the Atlanta Games in 1996 and again in Sydney in 2000. Can you tell me why you love kayaking?
Yeah, I really enjoy kayak paddling because it allows me to get out there in the nature like we are right now.
Is it true the first time you got in one of these, you had to be carried to the boat?
Yeah, actually, when I started canoe paddling, before I got into the kayaking, the coach had to lift me into the boat because I still had crutches, and so...
Did you have any fear?
Yeah, I was afraid because I had these big knee braces on, and I was afraid that I wasn't going to be able to swim. I would just sink.
Right, you could drown. After everything you'd been through, now you're going to get in a boat, yeah. You can't use your legs?
I think that competitiveness and wanting to do it and be a part of the team kind of overcame those simple, basic fears of being able to swim. You guys got me out of the cardiac arrest and help me progress in life.
These days, Cliff gives inspirational talks to firefighters, and especially to other burn victims, urging them to never give up. You think that's why you were saved?
I don't know. My mother believes that. And if I can help others, then I know I've done my job.
And he's just been named spokesman for the Construction Safety Council, hoping to lower the rates of electrocution in this country.
Okay, so he ended up jackhammering into 30,000 volts of electricity and survived to tell us about it. How do you survive something like this? All right, so let's just run the numbers real fast. So 30,000 volts of electricity. I'm going to go with what Mythbusters came up with. I'm going to assume that the human body's resistance is Mythbusters. Let's go with the Mythbuster reality. During stream, the human body, everything is at the same resistance. So if that's the case, what is the amount of current going through the body? All right, so let's come up with a naive estimate at first, and then let's make it a little bit more sophisticated. So whatever it is that we use, obviously we will be using the Ohm's law. All right, so what would be the amount of current going through the body if that's the case? All right, so I'll immediately know this is going to give you 3 amps of current. That's survivable or deadly?
Should be deadly.
It should be deadly. Yeah, I mean, I'm thinking that's too much. I mean, granted that by the time the current gets to the heart, it's not going to be 3 amps. It's going to be smaller. Even if it's smaller, it should still give him a heart attack, and he was having a heart attack. So this should be deadly. So, which means that this number cannot be correct. All right, so immediately I'm going to switch from Mythbusters to something a little bit more realistic. So I'm just going to go up to Wikipedia. All right, so Wikipedia has the more accurate numbers. Okay, we're not doing any physics labs in a laboratory, obviously, so we don't get to play with the resistance. Dry skin is 100,000. All right, so with their dry skin, a more realistic number is going to be, okay, so what we have? It's at, what is it, 3 amps of a current? Okay, so 3/10 of a current, amps of a current, would that be deadly? Yeah, it can give you a heart attack, and that's exactly what happened to him. He was having a heart attack at the time. All right, so exposure time is important, don't forget that. And the exposure time was a factor. It was part of the circuit for a long enough time. So what happened to his legs? Current going through the legs, obviously the bones didn't do too well. Okay, so there's nerve damage. There was damage to the bones and everything else, so he's no longer able to walk. So that's obvious. And the current definitely got to the heart, and he was having a heart attack. All right, so whatever the physics that we're developing so far, in a conceptual sense and somewhat mathematical sense, it's kind of working in a weird sort of way. All right, so the heart is defibrillating. Oh, he was having a heart attack. So what they do, they end up shocking his heart, right? All right, so in order to do that, they end up pumping about 20 amps of current into the chest cavity for about 0.02 of a second, while hoping that there's a decent amp of current getting to the heart in order to restart the heart. So it would just paralyze it. And then when you stop the current, it would be a reset. So the electrical rhythm would reset. So that's what happened. All right, so one of the questions that we had previously, and I'm going to have the same question. When you have a defibrillator like that, this is a capacitor in general. Notice that you can control the discharge period. It's 2,000th of a second. It's not 1 second, it's not 2 seconds. You don't want to kill the guy. It has to be calibrated just right. So how do you control the discharge time? Guys, it is exactly like lightning, except it's 100% control. How do you control the discharge time? You have the same question here. Notice that the flash goes up exactly the moment the bullet is going through the internet. All right, the discharge happens within 0.3 of a millionth of a second. That's precise. It's extremely well controlled. Once again, you're dealing with controlled lightning. How do you control the discharge time to this extent? What makes it possible? All right, so we're dealing with the direct current circuits. This stuff is fairly straightforward. We've been discussing it quite a bit without you guys knowing about it. Direct current simply means the current is flowing in the same direction. That's what it means. It's moving from a negative terminal to the positive terminal. If you go with my lecture, that's the direction that it goes. It goes from a negative terminal to the positive terminal. If you go with the books, it's going to go from a positive terminal to the negative terminal. All right, so traditionally, it goes from a positive terminal towards the negative terminal. That's it. All right, so this is known as a direct current because the direction of the current remains the same. Current only goes in a single direction, hence the reason why it's called a direct current. All right, so we have 3 resistors, 1, 2, 3. All of them are connected in series, so which means that the resistors are connected in series. So what is the overall resistance of the circuit? We came up with some kind of a conceptual understanding of it. Now we will have to do the same thing more mathematically. All right, so this requires a little bit of a derivation for this one. All right. All right, so we'll start with the Ohm's law. Voltage is what drives current, and resistance is what diminishes it. All right, so this is the total voltage that you get from the battery. This is the total current which is going to be going through each and every single resistor. And this is the total resistance that we're looking at of the system that we're going to be looking at. All right, so what's going to happen is the voltage from the voltage source, which is the amount of energy supplied, some of that voltage is going to drop across the first resistor, which means that the energy supplied is going to be lost. It's going to get converted into heat or light. Some of the energy is going to be lost in the form of heat or light for the second resistor, and some of it is going to be lost in the form of heat or light for the third one. All right. Instead of saying some of it is going to be lost in the form of heat or light, blah, 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 which means it's going to get converted to heat or light, or it's going to get converted into heat or light, or it's going to get converted into heat or light. You say there's going to be a voltage drop, there's going to be a voltage drop, there's going to be a voltage drop. When we talk about voltage drop, which means that the energy is getting converted into something else. So the electrical energy is being lost, which means that it's getting converted into something else. So electrical energy being lost means a voltage drop. This is the way we express it. So there's going to be a voltage drop across the first one. There's going to be a voltage drop across the second one. There's going to be a voltage drop across the third one. So that's the terminology that we're going to end up employing. All right, so the amount of voltage supplied by the battery is going to be equal to the voltage drop across the first resistor, the second resistor, and the third resistor. All right. This is otherwise known as the conservation of energy. The amount of energy supplied and the amount of energy lost, not destroyed, but the amount of electrical energy lost will be equal to each other. All right, so this is the conservation of energy principle. All right, so the amount of energy supplied by the battery and the amount of energy lost through each and every single resistor is going to be equal to each other. All right, so having said that, write this out. Amount of energy dropped across the first resistor, make this 1, make this 2, make this 3. The first resistor is going to be this, second resistor is going to be this, and the third resistor is going to be this. It is the same current that's going to flow through each and every one of them. So the current flowing through is the same. All of them have the same amount of current flowing through each and every one of them. All right, I1, I2, I3. I'm going to underlying assumption, mathematical assumption is there's different amounts of current flowing through each and every one of them. So I want you to know that the current flowing through each and every one of them is the same current. All right, so R1 plus R2 plus R3. Factor out I. So what we have, this is the total voltage, this is the total current, and this becomes the total resistance. All right, so the voltage is going to be R, I in this case, so this is going to be your total resistance. So the total resistance of the system is R1 plus R2 plus R3. All right, so when the resistors are connected in series, you end up with resistance values. We definitely arrived at the same conclusion last time by using the traffic analogy. Whatever resists the motion of the traffic is going to slow down the traffic. Larger the resistance is, the slower the traffic is going to move, which means that the resistance becomes additive when the resistors are connected in series. All right, guys, take a break for 10, be back in 10. All right, guys, pick out the best answer. All right, jump in whenever you're ready.
Hey.
All right, the overall resistance is going to go up. Give yourself 5 points for that one. Those of you guys who like that, give yourselves. Okay, the derivation itself is simplistic. I'm not interested in the derivation. It's just the details of how we arrive at some of these simple formulas. Okay, so in this case, what we have, everything is connected in parallel. All right, so R1 is parallel to R2, R3 is going to be parallel to R2 and R1, and so forth. Okay, so it's the current coming from the battery. So you will have these junction points. Some of the current is going to go this way, some of the current is going to go that way. Again, the current is going to split, and so forth. So the amount of current coming out of the battery is going to split into these branches. So the amount of current supplied and the amount of current that splits will have to be the same. All right, so this is known as the conservation of charge. When the resistors are connected in parallel to each other, the voltage drop across each and every single resistor is going to be the same as the voltage supplied by the battery, as if each and every single resistor is connected to the battery separately. All right, so that's what it means. Okay, so those are the basic rules. Once again, for the derivation, Ohm's law, voltage is what drives current, and the resistance is what's going to diminish it. In this case, the amount of current supplied by the battery is the same amount of current which is going to branch out. So the current supplied, all right, let's change this. And the current for each and every single resistor is going to be the same. All right, so this comes about because of the conservation of charge. All right, so this is your conservation of charge. And the voltage drop across each and every single resistor is going to be the same as the battery. All right. Having said that, so we will get to use the conservation of charge, this stuff, to figure out the total resistance of the circuit. So the current across the first resistor, which is this, is going to be the voltage drop divided by the first resistor value. The current across the second one, and the current across the third one. All right, we know that the voltage drop across each and every single resistor is going to be the same as the total voltage supplied by the battery. All right, so which means that we can rewrite this formula in this fashion. So what do we know? Since, according to the Ohm's law, the current supplied is going to be directly related to voltage and inversely proportional to resistance, total resistance is going to be the same as the inverse sum of each and every single resistor that we have. All right, so that's it, resistance of, so the total resistance of resistors in parallel is going to be expressed in terms of the reciprocal of the total resistance as every single resistance is added reciprocally. All right, so mathematically it works out. I want you to convince yourselves that the total resistance here is going to be smaller than the smallest resistance of each and every single resistor. All right, guys, imagine that the first one is 1, the second one is 2, the other one is going to be 3. All right, so this is going to be 1, this is going to be, what is it, half, this is going to be a quarter. So the total resistance of this is going to be smaller than the individual resistance values of each and every single one of when you plug the numbers in.